Okay, and so then the first talk in this session is by Thiago Felicissimo, generic bidirectional typing for dependent type theories. Please.
Thank you, Thorsten. Okay, so let me start. Let me start by talking to you about the syntax of type theory. So when we're defining programming languages and type theories, we have a choice to make with respect to which syntax we want to use. So one possible choice is, for instance, to use a fully annotated syntax in which we keep track of all of the typing information in the syntax. So for instance, whenever we have an application, we write the domain and the codomain of the application. And this is a very natural choice. Maybe, is it better like now? Okay. So this is a very natural choice because this is the syntax that you get when you see it as an algebraic theory, type theory as an algebraic theory or in a logical framework. And I think that is arguably the most canonical choice because if you need to choose which annotations you're leaving out, it's better to choose to leave everything. But of course, this syntax is not very usable in practice. Not only it's like slower to type check and reduce terms which are fully annotated, but of course you cannot ask users of type theory to write all of this stuff. So what we use in practice is like non-annotated syntaxes, but of course there are many levels of which annotations you can omit. Here I'm omitting the parameter annotation, so we write application and dependent pair like the way that we're more used to. And this is a syntax that is so common that we don't even sometimes realize that an omission is being made, but it is. And we see this when, for instance, looking at typing, because this omission has a cost, because knowing annotations is needed for typing. If we're trying to build the type derivation bottom up and you do not have like the types, then how do I fill the question marks there? Like somehow I need to guess A and B. And bidirectional typing is all about answering why you do not need to guess, but there's a way of recovering these annotations. The idea is to decompose the regular typing judgment into two modes, the check and inference modes. And now this allows you to specify algorithmically how the type information should flow in typing rules. So for instance, if you want to infer the type of this, you start by inferring the type of the head of the application. Then you try to reduce it to find the parameters. You can check that the other term then is typed by A, and now you return B, where you replace X by U. And this complements the non-annotated syntax that we want to use very well, because it really explains locally how we can recover these annotations. Okay, so bidirectional systems have been studied for a lot of time, so there's a lot of work in proposing bidirectional systems for different theories. At the same time, the general guidelines have remained informal, and there's no unified framework for bidirectional typing for dependent type theories. So this is exactly the goal of this talk, to give a generic account of bidirectional typing for a class of dependent type theories. And the roadmap will be the following. So I'll start by giving you a general definition of type theories, or equivalently, if you want to see it that way, a logical framework, which supports the non-annotated syntax that we want to use, because of course bidirectional type is only interesting when we omit the annotations, otherwise you don't need bidirectional typing. And for each theory, we will define declarative and bidirectional type systems and then show in a theory-independent fashion that they're indeed equivalent. So let me motivate them more why this is, I think that this is an interesting problem. So I think that personally that theoretically is already something that is interesting, but can also have practical applications. So in particular, I implemented the framework that I'm going to present here in a theory-independent bidirectional type checker, which I call BITS. And this is like a fragment of a definition that you can do inside of it. So here you're defining equality type, and then you're showing some basic properties. And as you can see, you indeed do not write all the annotations when you write in terms inside of the theory. And you have many theories which are supported, so flamers of MLTT, some sorts of observational type theory. I'll refer you to the implementation for more details. So yeah, I think that this not only can allow you people to like prototype with new ideas of type theories without having to implement a bidirectional typing algorithm from scratch, but also compared to other like theory-independent type checkers like deducti and Andromeda, I expect that the non-annotated syntax should allow for better performances, and this might be a good candidate for having a type checker for cross-checking proofs like in the deducti project. So yeah, so let me jump into the definitions of the framework. So I'll start by then defining what are the theories that we have. So we have some kind of entries. We have the schematic typing rules and the rewrite rules. And then the schematic typing rules are separated into three types. You have the sort rules, the constructor rules, and the destructor rules. So let me start with the sort rules. So in the framework here, I will call a sort a term that can appear to the right of the typing judgment. So you might find this a bit strange, like why don't you call them just types like we normally do? But I'm trying to avoid a name clash with the types of the theory, so just accept this choice, please. And then the idea is that they allow us to represent the judgment forms of the theories we define. So if you know, for instance, GATS and SOGATS, this is the same idea. So for instance, in Morting-Loft type theory, we have two judgment forms. We have the judgment form that asserts that something is a type, that asserts that something is a term of a certain type. And these are defined in the framework this way. So actually, this is just an informal notation for this. So this is the real definition of what is a sort rule. It's a constructor and a meta-variable context. So I'm not going to give the syntax for the meta-variable context. I'm going to trust your intuition for what these are, because I don't have the time. But so these are the formal notations for the sort rules, and we can parse these into the formal notation as these. I hope that it's clear, the correspondence. Okay, so this defines the sorts of the theories. Then we should also define the terms. But the thing that is special with bidirectional typing is that the way that we're going to recover the missing arguments very much depends on whether our term starts by a constructor or a destructor. So we're going to have two separate cases. So we're going to have the constructors and the destructors. So let's start with the constructors. So in bidirectional typing, constructors support type checking. So the idea is that you should check the term with a sort, and the sort will be used to recover the annotations that are missing. And to capture this, we're going to separate the premises of the rule between the premises that are erased and that are kept in the syntax. And then we should require that the sort of the rule should be a pattern on the missing meta variables. So let me just say that the pattern here is not on the usual sense. There are some restrictions. Notably, it should be linear, and we should only have constructors in the pattern. And okay, so we have two examples of constructor rules. We have, for instance, the rule for the pi type, which is a bit degenerate case because this is a pattern with no meta variable, so there are no omitted arguments here. And then we have the abstraction, and here we see that A and B are the meta variables of the pattern, so they do not appear in the syntax. And okay, so formally, the constructor rules are of this shape here. And this is the way we can parse these rules here. And then we have the destructor rules. So contrary to constructors, destructors, they will support type inference. So the way you're going to get the missing information is by inferring the sort of the principal argument, which is a special argument of the rule. So like before, we're going to separate the premises into a meta-variable context, the ones which are erased and the ones that are kept in the syntax, but we're also going to have a special argument, which is the principal argument, and whose pattern should allow us to recover the missing information. And of course, the main example is the destructor rule for function type, which is application. And here we see that indeed the principal argument, which is always the first non-erased argument, has a sort, which is a pattern allowing us to recover the A and the B here. And yeah, formally, they are of this shape here. So a destructor, the missing arguments, the principal argument, the arguments that are not missing, and this is the output sort of the rule. And this is the way we can parse this into the formal notation. And finally, we have the rewrite rules, which will allow us to define the definitional equality of the theory. So here I'm not supporting type director rules. I'm going to mention a bit why at the end of the talk. But then we can define, for instance, the computation rule for the function type, the beta rule. And they're in general of this shape, so you should be headed, of course, by a destructor, and then you should have only patterns with a constructor in the principal argument. And there's a supplementary condition, is that no left-hand side should unify. So basically, what this guarantees is that the rewrite systems that you have are orthogonal and hence confluent by construction. And yeah, so this finishes the definition of what are the theories. And if we pack all of the things that we saw as examples, then we get this theory here, defining a very basic Morton-Loft-type theory with only function types. So yeah. So now that we have the theories, we can look at the type systems of the theories. So like I said, the theories, they contain schematic typing rules, but we can instantiate them. And this yields the main type system, which we would just say the type system if there weren't two, because they're the bidirectional ones. So here, I'm going to call it declarative, just so we know which one we're talking about. So each theory defines, like I was saying, a declarative type system. And the main rules here, I'm not going to show all of the rules, but they instantiate the schematic rules of your theory. So this is the rule which instantiates the schematic destructor rules. Instead, let's just look at an example rather. If we instantiate with the destructor, with the application rule from the theory we had, then we get indeed what is the usual rule for application, except that we have these three premises at the top which are admissible from the fourth one. So this is why we can normally omit them, but normally they should be there. And yeah, so the thing that you should remark is that reading bottom up, if you're trying to build a type derivation, then you have to guess A and B, and this is what the bidirectional type system is going to, this is the problem that it's going to address. Yeah, and finally, some properties of the declarative system. So this is in the paper. There certifies the desirable properties that we would expect, such as weakening, substitution, and subject reduction. And they're not only good sanity checks for having sure that this is a well-behaved framework, but also because they're important when showing the equivalence between the declarative and the bidirectional type system. Okay, so let's jump into the bidirectional type system then. Before giving you the definition, we first have to see this, because so to recover missing arguments in bidirectional typing, we actually need to do a matching modular rewriting. And to understand this, let's look at this situation here. We're trying to infer the head of an application. And then if your term is well-typed, in the declaratively well-typed, then you know that this should be convertible to an instance of this here. But of course, they're not syntactically equal, they're just convertible. So you need to find the substitution modulo, the conversion generated by the rewrite rules. And I'm not going to give the definition, but I'm just mentioning because we will need this for the bidirectional system. We specify an algorithmic matching judgment here, algorithmic in the sense that is decidable when the term U is normalizing, which allows us to recover a substitution exactly when. Okay, so actually you recover a substitution that is convertible to the one that you applied here. This is a small subtlety that I didn't write. Okay, so a second thing that we need to address is that not all terms without annotations can be algorithmically typed, and this is the main example to understand why. If you're trying to infer the type of a beta redex, then you're going, so I mentioned that for a destructor rule, you always infer the sort of the principal argument, then you're going to try to infer a lambda, but lambda is a constructor, it only can be typed in mode check, so this is, you're now stuck, so what should you do? And the idea is that you should not define the bidirectional system for the same syntax which you use in the declarative system, but instead you should define it for the bidirectional system in which you separate between inferable and checkable terms. So what is going to be inferable here is going to be variables, because of course you know their source, just look up in the context. destructors because they can be inferred. And also, if you want to turn a checkable term into an inferable one, you also have the operation of sort ascription. And now if you want to write beta redexes, they cannot be written directly, but instead you need to add a sort ascription, like in the works of Conor McBride. So this is the way that you should write whenever a destructor meets a constructor, you need to insert an annotation there. Okay, we have all of the ingredients needed to see the bidirectional type system then. So just like with the declarative one, each theory defines a bidirectional system, and the main judgments are the check-in and the inferring judgments. So one thing that I would like to point out is just that all of the other constituents of the typing judgments are declarative, are from the declarative syntax. Only the thing that you're typing is bidirectional. So all of these are, for instance, this is a declarative sort. And yeah, just like with the declarative system, the main typing rules are going to instantiate the schematic rules of the theory. So once again, let's not look at this, but instead look at an example. If you instantiate, for instance, the previous rule with the application rule from the theory, from this theory here, then you get exactly what would be the usual bidirectional rule for application. So here you start, you have an inferable term, you infer it, you get a sort. You're going to do matching to recover A and B. Then you can check U, and then you return the sort here. And I'm writing this because this is U and T here are bidirectional terms from the bidirectional syntax, and I need to recover the underlying declarative term, which is you just erase the ascriptions, and this is what it is doing here. So yeah, the thing that you should remark is that reading bottom up, you don't need to guess A and B anymore. They're recovered algorithmically. Okay, so this is a condition that I'm omitting here because to simplify the talk. So let's forget about this. It's in the paper. We have then the correctness with respect to the declarative system. So the first part, which is soundness, says that if the declarative system infers a sort for a term or type checks a term, then this typing judgment is indeed true. So here I forgot the hat here. This is just a detail. Then the judgment is also true in the declarative system. And then we also need a notion of completeness, and completeness here corresponds to annotability. So if you have a term that is declaratively well typed, then you can find a way of annotating it such that when you remove the annotation, you get what you started with. But then this is checks in the bidirectional system. And of course, the interesting property of the bidirectional system is that it is decidable under suitable conditions, namely the theory should be normalizing, because you need this to decide definitional equality. So under these conditions, the bidirectional system is decidable, so it allows you indeed to use it as in an implementation. Okay, so I'm almost finished. I just wanted to show you some examples so you know that we can do more than just function types, but you're not supposed to read through all of them because there are many details. So you can do, for instance, dependent sums, and here note that on the projections and the constructor, you do not annotate with the parameters. This is the syntax that you want to write. We can do lists. Yeah, in general, any inductive type. We can do equality, but there is a small but here, because this is not a pattern in my sense, because I mentioned that I require patterns to be linear. And actually, in general, you have this, the definitions that I presented here, they do not work with the index types in general. So in the paper, the modifications that you need to do to cover index types are explained, but I choose to not cover them here because it's a bit more complicated. But the intuition here, or the idea very roughly, is that you're going to split the meta variables of the sort here into the parameters meta variables and the index meta variables. and you should have an index substitution, which is going to explain what are the values of the index metavariables using the parameter metavariables and the constructor metavariables. Yeah, so this is the rule that you get for reflexivity when in this framework. And then, of course, you can also do other index types, like, for instance, vectors. And here, you specify that n should be 0 and that n should be successor of m for indices. And you have some other examples that you can look you can see in the implementation if you want to see them. So, for instance, higher order logic, you can have many types of universes, have a flavor of observational type theory. So yeah. Okay, let me conclude then. So we have given a generic account of bidirectional typing for a class of dependent type theories. This is implemented, so I invite you to check the implementation if you're interested. Let me say a couple of words about future work. So I mentioned that I expect that the fact that this yields a theory-independent type checker, which allows you to omit the annotations, should yield better performances compared to, for instance, deducti. So yeah, I still need to check this practically with real proof libraries to see the real performance gains. But I think that this is, like I mentioned, a good candidate for like a theory-independent cross-checker. Then I also mentioned that I do not cover type-directed rules here. And the reason is that, well, if you only have rewrite rules, then you can decide the differential equality in a homogeneous, in a uniform way. If they're confluent and strongly normalizing, then you know that just calculating normal forms and comparing them is a complete strategy. And even though we can design equality checking algorithms for type-directed equalities, I do not know of an approach that to do this generically like we know with computation rules. A different approach would also be to treat conversion with a black box. So you just say, I have this thing which you need to instantiate if you want to use the algorithm. So this is an idea that we started exploring with Maven. And also in a related topic, so I think that some of you might have objections with respect to the declarative type system here. So many people prefer to think as the definition of a type theory should be the initial model with respect to some logical framework or some algebraic, like some GAT or SOGAT. So like a question that I think is interesting is, can we replay the same thing but with a more abstract declarative type system? So for instance, maybe this could yield like a kind of generic bidirectional elaboration for a class of SOGATs. I don't know, I think that this is could be an interesting possibility to explore. So yeah, this is what I had to say. Thank you.
Okay, thank you. Can we? Okay, are there any questions, especially long and difficult questions which require long answers? They would fit perfectly in our timing, no? Okay, anybody? Yeah?
Try to make it a bit longer for you. So at some point you said that you wanted to have these reductions in the style of McBride, where you had an annotation on the thing being eliminated.
So no,
but then you moved away from that again, right?
The reductions the rewriting are not defined on the annotated terms. So for instance, what the reduction rule that Connor would write would be would be on the annotated terms. So this would yield U in which you need to add an annotation in the thing you substitute and on everything. But here annotation reduction is on the declarative type system. So there are no annotations there.
Right. Okay. So you want this in the syntax, but
yeah, but there's not even substitution that is defined for this, for the bidirectional system syntax.
Okay. Are there any? Actually, I think you almost answered my question with the last point. But why would it not work for SOGATs in general? Is it only for Tim and Tai, or can you also put in other SOGATs?
Oh no, it works for other theories. But what I mean by SOGAT is that. is that so for the declarative type system here, you still use non-annotated terms and untyped equality, and I think that what most people would mean by SOGAT, it would be like a fully annotated syntax, even maybe quotiented terms, as I know you like. So, like doing this is like the question that I was asking more.
But in principle, I have a SOGAT I'm interested in, and you would be able to do this.
Well, not of all SOGATs, of course, but the idea would be say, which class of SOGATs could we?
Yeah, no, but potentially. I mean,
yeah,
okay.
But yeah.
Thank you.
Yeah.
Thank you. What? Yes. Mic is on. Yeah. Okay. Let's thank the speaker again.